Hi again. So far we've talked about the binomial coefficients, we gave some examples, how to calculate them, and we also talked about a couple of the properties. Now we want to continue with some more properties and talk about the Pascal triangle and the binomial theorem. Okay, so first let's start with Pascal's identity that says that n plus 1 choose k is n choose k plus n choose k minus 1. And for example, 4 choose 3. If we take n to be equal to 3 and k to be equal to 3, then 4 choose 3 is equal to 3 choose 3 plus 3 choose k minus 1, namely plus 3 choose 2. Okay, and to see why that is so, observe that 4 choose 3 denotes number of sequences of length 4 with 3 ones. So here we have all binary sequences of length 4 with 3 ones, and we can decompose this collection of sequences into two subsets, into two smaller collection. One where the last bit is 1, like this, and one where the last bit is 0. So we can write it as the collection of all binary sequences of length 4 with 3 ones where the last bit is 0, and the collection of all binary sequences of length 4 with 3 ones where the last bit is 1. So these two together, these two sets are disjoint, and together they give us everything here, because every sequence here has length 4 with 3 ones, and either the last bit is 0 or the last bit is 1. So we just partition this set into two subsets, and therefore the sum, the number of elements here, which is 4 which is 3, sorry, plus the number of elements here, which is 1, will give us 4, which is the total number of elements here. So the only question is how many elements we have here and how many elements we have here. So how many elements we have here? Well, the last bit is 0, so that means that we have 3 ones in the first 3 locations, and the total number of such sequences is 3 choose 3, because we have 3-bit sequences with 3 1, and there's 3 choose 3, namely a single 1 sequence here. So we have 3 ones. And how about this set? How many elements are here? Well, we have all the strings here of length 4 with 3 ones, but we're using 1 bit here. So here we have this set corresponds to the collection of 3-bit sequences with 2 ones. So here we have the collection of 3-bit sequences with 2 ones, and we just appended each of them with 1. So we're asking how many 3-bit sequences have 2 ones, and that number is 3 choose 2. So we get that the collection of 4-bit sequences with 3 ones, this collection here, corresponds to the collection of 3-bit sequences with 3 ones. That's a collection here, which is 3 choose 3, plus the collection of 3-bit sequences with 2 ones, namely 3 choose 2, which is the number here. And this will hold, in general if we consider binary sequences of length n plus 1 with k ones, then they'll consist of binary sequences of length n plus 1 with k ones and 0 at the end, and that number is going to be n for the first n location, choose k, because we still have the same k ones, plus the number of sequences of length n with k minus 1 ones, and those will correspond to the sequences of length n with where the last bit is 1, so we have k minus 1 ones in the first n locations. And when you sum those up, you'll get n plus 1 choose k. Okay, so this is Pascal's identity, and we can use it to create Pascal triangle, which is a way to calculate all the binomial coefficients, again in a different recursive way. So as we have seen, n plus 1 choose k is n choose k plus n choose k minus 1. So we can start writing the Pascal triangle by first writing, so this is going to be, the rows will correspond to n and the columns will correspond to k. And we know that n choose 0 is 1, and that means that this first column is all ones. Okay, so this is, for example, 5 choose 0, which is 1, 4 choose 0, which is 1. And the first row will correspond, the diagonal here will correspond to n choose n. So for example, this is 0 choose 0, this is 1 choose 1, this is 2 choose 2, and so on. So n choose n is 1, and therefore this corresponds to all ones. And now when we want to use this identity, then for example, if you want to calculate 2 choose 1, then according to this identity, 2 choose 1 is going to be 1 choose 1 plus 1 choose 0. Okay, which we can draw here. 2 choose 1 is 1 choose 1 plus 1 choose 0. Okay, this is 1 choose 1, this is 1 choose 0. We have to add them up. And then if we want to calculate 3 choose 1, it's going to be 2 choose 1 plus 2 choose 0. So that's this number here. 3 choose 1 is going to be 2 choose 1 plus 2 choose 0. So it's 2 plus 1, which is 3. And if you want to calculate 3 choose 2 by Pascal's identity, it is going to be 2 choose 2 plus 2 choose 1. So that's this number here. It's 3 choose 2 is 2 choose 2 plus 2 choose 1, or 1 plus 2, which is again 3. And if you want to calculate 4 choose 1, it's going to be 3 choose 1 plus 3 choose 0, 3 plus 1, which is 4. If you want to calculate 4 choose 2, it's going to be the sum of these two, which is 6. And this value here is going to be 1 plus 3, which is 4. And so on. We get 5, namely 4 plus 1, 10, 6 plus 4, 10, 4 plus 6, and 5, 1 plus 4. Okay, so this is Pascal triangle. It shows in row n and column k. It shows n choose k, and also we have a recursive way of calculating it by having each element as the sum of the element above it and the element diagonally to the left of it, up and to the left of it. Okay, so when you observe the Pascal triangle, it has many properties, and here's one property that is quite apparent. So here is the Pascal triangle again. If we take a plus b and raise it to the first power, a plus b to the 1, we just get a plus b. Okay? If we take a plus b square, we get a squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, and so on. A plus b to the 4, a to the 4, 4a cubed b, 6a squared b squared, and so on. And when we look at those the coefficients, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, then they're exactly the same as the coefficients here. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. In other words, what this suggests is, and that the coefficient, if we take, for example, a plus b to the 4, the coefficient of a to the 4 is going to be 4 choose 0, which is 1. The coefficient of a cubed b is going to be 4, which is 4 choose 1. The coefficient of a squared b squared is going to be 4 choose 2, which is 6. The coefficient of ab cubed is going to be 4 choose 3. The coefficient of b to the 4 is going to be 4 choose 4, which is 1. Okay, and writing this out, it means that if you take a plus b to the nth power, is going to be the summation of I going from 0 up to n of n choose I times a to the n minus I times b to the I. In this case, a plus b to the 4 is going to be 4 choose 0 times a to the 4b to the 0 plus 4 choose 1 a cubed times b to the 1 plus 4 choose 2 a squared plus a squared b squared, and so on. And in general, a plus b to the n, again, summation I going from 0 to n choose I, a to the n minus I times b to the I. Okay, so this is what we get by observation, and we want to explain why this is the case. Okay, so and in general, let's first repeat it. We said that a plus b to the n is summation of I going from 0 to n of n choose I times a to the n minus I b to the I, and that holds for every a and b and every integer n which is bigger than or equal to 0. And this is actually a quite important theorem. It has many applications, and for one thing, it gives the binomial coefficients their name, because what we have here are polynomials with two variables like a plus b to the n. If you want, you can have a plus x to the n, or x plus y to the n. So you'll get polynomial with two variables, and polynomials with two variables are called binomials. And that's why this is called the binomial theorem, and that's why these coefficients are called binomial coefficients. All right. So let's explain where the binomial theorem comes about. So let's look again at an example. Suppose we take a plus b cubed, which is a plus b times a plus b times a plus b. And then notice that we have three factors. Each of them is the same, a plus b. Now, when we factor things out, we'll get a times a, or a cubed, plus a squared b, plus aba, and so on up to bbb. In fact, we'll get 8 such terms. Okay, and each term we get by selecting one of the a and b from each of these three factors. Okay, so we get a sum of terms and in fact we have 8 terms, and each term is a product of a's and b's, where one's selected from each of the 3 factors. Okay, so for example, a b we got by selecting this a, and then this a, and this b. Okay, so notice that in all of the terms, they consist of a's and b's, 3 in total, and so the number of a's plus the number of b's is 3 because we have 3 factors and we chose 1 element from each. Okay, and furthermore, if we're going to group the terms together, so how many times we have a cubed? We have 1. How many times we have a squared b? We have here a squared b plus another a squared b here plus another a squared b here. Okay, so we have 3 terms, and we have 3ab squared from this one and from this one and that one, and we have a single b cube. And these numbers that we are looking at, the numbers that multiply each term here, are what we want to show are the binomial coefficients. Okay, so how many terms are there with IBs? That's the number of ways of selecting I factors out of the 3 factors that we have here. So for example, here if we want to see how many ways we can select, how many terms have a single b's, then remember we need to choose either a or b here, or a or b here, or a or b here. And the number of ways of selecting a single b is the number of ways of selecting 1, because we're looking at a single b, out of the 3 terms here. And if we consider the number of ways, the number of terms that will give you ab squared, that will be the number of ways of selecting 2 b's out of these 3. So 2 factors out of the 3, and that's going to be 3 choose 2. So the number of terms with IBs is the number of ways of selecting I factors out of the 3, which is 3 choose I. Okay, so for example, 3a squared b, and then it's this one, or this one, or this one. Okay, and it corresponds to selecting either this b, or this b, or this b here. Okay, and this will tell us that this number is going to be 3 choose 0, number of ways of selecting 0 b's, times a cubed, plus 3 choose 1, number of ways of selecting a single b, times a squared b, plus 3 choose 2, ab squared, plus 3 choose 3, b cubed. Right? And generally, we get that, so we just saw that a plus b cubed is this term here, and generally, which is summation I going from 0 to 3 of 3 choose I, a to the 3 minus I, b to the I. And similarly, if we have a plus b to the n, it's going to be n choose 0 times a to the n. That's how many ways we can select. We have n terms. We need to select 0 b's. And here we have n terms. We need to select a single b. That's n choose 1. Here we have, again, n terms. We need to select n b's, and that's n choose n, which we can write as summation I going from 0 up to n of n choose I, a to the n minus I, b to the I. Okay, so this is, if you want, a proof of the binomial theorem. Okay, and now we want to see a couple of applications. So remember that we said before that summation of n choose I is 2 to the n, and we proved it combinatorially by saying this is the total number of sequences of length n, and this counts the number of sequences of length n with I ones. Okay, and we give a combinatorial proof, which is basically what we have just said. And if we want to give an algebraic proof, then notice that 2 to the n, this number 2 to the n, is 1 plus 1 to the n. And according to our formula, it's going to be summation of n choose I to the n, 1 to the n minus I times 1 to the I. But 1 to the n minus I is 1, and I to the 1 to the I is again 1. So we get that this is equal to summation of n choose I. So that's a simple proof that 2 to the n is equal to summation of, from I going from 0 to n, of n choose I. Okay. Another application of this theorem is to find coefficients of polynomials. So suppose we take 1 plus x to the n, then by the binomial theorem, it's going to be equal to summation I going from 0 to n of n choose I times x to the I, and then 1 to the n minus I, which is 1, so we don't write it. So it's summation of n to the I, x to the I. And now we could ask, what is, for example, the coefficient of x squared in 1 plus x to the 7? Okay, so 1 plus x to the 7 is summation of I going from 0 to 7, or 7 choose I, x to the I. That's what we said here. Okay, and what is the coefficient of x squared? We need to look at the coefficient of x squared here, and that's going to be just 7 choose 2. Okay. And 7 choose 2 is 7 times 6 divided by 2, which is 21. And one could factor this out and verify that the coefficient of x squared is 21. Okay. Similarly, what is the coefficient of x cubed in 3 plus 2x to the 5? Well, we can write this using the binomial theorem. 3 plus 2x to the 5 is summation I going from 0 to 5 of 5 choose I, 3 to the 5 minus I times 2x to the I. Okay. And we're interested in the coefficient of x cubed, so we're interested in what happens when I is equal to 3. And when I is equal to 3, the coefficient is going to be 5 choose 3 times 3 to the 5 minus 3 times 3 square, and then times 2 to cube. So 5 choose 3 is the same as 5 choose 2, which is 5 times 4 divided by 2, which is 10. And 10 times 9 times 8 is 720. Okay. And one more application is to show how we can use the binomial coefficient to get the Taylor expansion, at least of e to the x. So we know that e to the x is equal to summation of I going from 0 to infinity of x to the I divided by I factorial. And we want to derive this expansion not using calculus, but just using combinatorics. So notice that one definition of e to the x is 1 plus x to the n over n. For example, one definition is 1 plus 1 over n to the n when n tends to infinity. And e to the x, by the same reasoning, is 1 plus x over n to the n. Okay, so we can expand this using the binomial theorem. So this is going to be equal to summation of n choose I times x over n to the I. And there's another term 1 to the n minus I, which we don't write because it's 1. So 1 plus x over n to the n, therefore, is equal to summation of n choose I, x over n to the I. Okay. Now, we can expand this out. So n choose I is n to the I falling power. Remember, that's n times n minus 1, and so on up to n minus I plus 1, or it's n divided by n minus I factorial. And then we need to divide by I factorial, and times x over n to the I. Okay, and we can just rearrange terms here. So it's equal to x to the I divided by I factorial times n to the I falling power divided by n to the I. Okay. So what we can do next is see what happens when n goes to infinity, right? Because we need to take the limit of this as n goes to infinity. So when n goes to infinity, this will tend, as we said by definition, will tend to e to the x. Okay. And how about the right side? So we have here the summation of I going from 0 to n of x to the I divided by a factorial times n to the I falling power divided by n to the I. But now let's see what happens to this term. This term will remain. Okay. But this term, n to the I falling power I, n to the falling power I divided by n to the I, will just tend to 1. For example, if you take n to the second falling power, we'll get n times n minus 1 divided by n factorial. But the difference between n minus 1 and n, would be n times n minus 1 divided by n square. But the difference between n minus 1 and n, the ratio goes to 1. So this n to the I falling power, n times n minus 1, would be roughly the same as n square. When you divide, it will give you 1. And if you have n to the third falling power, you have n over n times n minus 1 over n. N minus 1 over n will go to 1 times n minus 2 over n. Again, that goes to 1. So this will just become summation of x to the I divided by I factorial. And you just need to argue that you can exchange the limit and the summation, which you can in this case. Okay, so we get that e to the x is summation of x to the I divided by I factorial, which is the Taylor expansion, and we got it from the binomial coefficients. Okay. The last application of the binomial theorem that I want to mention is for the binomial distribution. We'll talk about the binomial distribution in a few lectures from now, but for now I just want to state the identity that will explain what will happen when we talk about this distribution. So, let's look at this summation from I going from 0 to n of n choose I, p to the n minus 1 times 1 minus p to the I, where p is any number between 0 and 1. Well, we know that by the binomial theorem that this is going to be just p plus 1 minus p raised to the n, right? Because this is summation I going from 0 to n of n choose I, p to the n minus I times 1 minus p to the I. But p plus 1 minus p is 1, so that just gives us 1 to the n, which is 1. So we get that this summation is 1. For example, if we take 1 cube plus 2 times 1/3 times 2 over 3 plus 2 over 3 square, okay, so that's an example of this where p is equal to 1/3, and 1 minus p is equal to 2/3, and n is equal to 2. So so we get that this summation is going to be equal to 1, right? Because it's in this case it's going to be 2 choose 0 times 1/3 square times 1 minus p to the 0 plus 2 choose 1, which is 2, times 1/3 times 2/3 plus 2 choose 2, which is 1, times 1/3 to the 0 times 2/3 to the 2. Okay, and that's going to be equal to 1. Okay, and we will use this identity when we talk about the binomial distribution, which is one of the reasons why we're mentioning the binomial theorem. Okay, so we'll talk about more then. Okay, so with that, we talked about different quantities of the binomial coefficients. In other words, we talked about binary sequences or choosing a subset from a set of size k. And what we want to do next is talk about larger alphabet sequences also for larger alphabets. And that's what we'll do in the next lecture. See you then.